Good morning, class. Welcome to October. Um, let's start our lecture because it's a minute past the starting point. I'm sure I don't need to remind you, but just a quick reminder anyway. Homework 2 is due today, and it deals with linear models, expressiveness, and mistake-bound learning and perceptron. And as always, if you haven't started implementing it yet, if you haven't started the homework, after class would be a good time. There's a ton of discussion on Canvas. Please take a look at it, and your questions may be already answered there, or if not, do join in. And also, I noticed something very nice. People from the class are helping each other and answering questions and such things, and that's fantastic because one of the nice things about having a large class around what I consider still to be a specialized topic is it builds this community of people who are interested in the thing and can help each other. Uh, According to the schedule, those of you who'd been following, homework 3 was supposed to be released today, but I've decided I'm going to delay it till Tuesday just to kind of reset the homework cycle a bit. Homework 3 will be a little different from homework 2 and 1. It's going to be entirely on Canvas. It will involve about 20 to 30 multiple choice questions on Canvas, and it's not going to cover the last week of material or anything. It's going to cover everything that we've covered so far, just to kind of make sure that we are all on the same page. One of the reasons homework 3 has this form is because after next week we'll be kind of slightly shifting gears a bit. We'll be moving into a more theoretical mode for a week or two. And then after that, we'll talk about what I think of as slightly more modern machine learning. The stuff you saw so far is from, say, the 80s or sometimes even the 50s. The new stuff might be from the 90s and 2000s and maybe even this decade. So homework 2 is going to be, it will show up as a quiz on Canvas, but it's not a quiz in the sense that it's not timed. You'll get 2 attempts at it, just like your homework 0. It uses the mechanism of quizzes on Canvas, but it's not a quiz in the sense that it's timed. So watch out for it. And you won't get the usual 2 weeks for that because it's little less work because there's going to be no programming. You'll get a week for the homework 3, and it'll serve as an opportunity for you to review what we have seen so far. Are there any questions either about homework 3 or about homework 2, about perceptron and such things? Question about homework 2. Does it matter for grading which hyperparameter is selected? Are you looking for a specific hyperparameter? Not really. So I'm looking more for accuracy to be in the right range. If you, for example, here's a good sanity check. Let's say that you run your code twice, and this was a question that others also asked, so I'm going to answer a broader question. Let's say you run your code twice, and because of some randomness that you didn't control for, the hyperparameter that gets chosen is different each time. What is perhaps more important than the actual hyperparameter that's chosen is the cross-validation accuracy. They should be close to each other because if different runs select different hyperparameters, the cross-validation accuracies for those 2 hyperparameters must be similar. Otherwise, something funny is going on. So we'll look more at the accuracies and the cross-validation accuracies as we are grading. We will notice that some people have a choice of have chosen this hyperparameter, whereas some people have chosen that hyperparameter. But then we'll also see the cross-validation accuracies to see if they are close to each other for these 2 choices. If that they are, then you're fine. Something that will not fly is, let's say you choose a hyperparameter. I'm just going to pick a number. I don't know what the real numbers are. Let's say you choose a hyperparameter of say 0.1, and you get an accuracy of 60%, whereas everyone else gets a cross-validation accuracy of maybe 75 or 80. Then that's a problem. However, let's say you choose 0.5 and everyone else, and you get 79 and everyone gets like 80, that's fine. If your accuracy is better than average, if it is shockingly better than average, that's also a problem. So if your accuracy, if your original, if let's say again, if the class, if a few runs of our own and also many of the students in the class get like 60% accuracy, and you report 95% accuracy. The problem is that it's not, since we know what the data is, we control it, and since we know what the algorithm is going to do, some kind of extremely high accuracy is also problematic. In this case, for example, some people reported getting 100% accuracy, for instance, and that's a problem. 100% accuracy, I don't think you can get 100% accuracy on this data set. Maybe my TAs can correct me on this, but I don't think you can get 100% accuracy. So extremely high accuracy is also suspicious. And when I say suspicious, I mean it is it's problematic, and it's not you're not really doing you're not learning. It's memorization of some data. So there was another question: how much is the extra credit worth? I don't remember anymore. Maybe one of my TAs can look it up and tell me. If it's not mentioned, I'm going to just mandate that it's say about 10 points, 5 or 10 points. I can't remember the reason. Maybe one of my TAs can look up and answer the question. There's another review question. Is the cross-validation accuracy the average accuracy on the withheld parts of the training set? It's the average accuracy across all the cross-validation folds. So yes. I don't know what that comment was about overfitting, but I think it was an answer to something else. Yeah, okay. Yes, so yeah, if you get extremely high accuracy, yes, you're probably overfitting, and that's not a good thing. Any other questions about the homework? What's the usual effect of accuracy on okay, so this is an important question, and I realized during my office hours there was actually a tiny error in the homework which might cause this to happen. So let me explain this and give you the two options and tell you what's going on. So let's think about the perceptron algorithm. So the question, let me just reread the question for the sake of the video. What's the effect on accuracy of decaying the learning rate? Mine drops a fair amount, and I'm not sure if that's normal. So let's look at the perceptron algorithm. So you have something like your weight, your initial. I'm just using the simple perceptron algorithm to illustrate what's going on. So you initialize your weight vector to the 0 vector, and then in this case, you set you initialize the t to the number 0, and then for in and so on. Okay. So you shuffle data, and then for x comma y in data. I'm just going to write perceptron update. I could have written the actual update with fewer letters, I think. And then, so let me write in blue the two possible options. But actually, so let me move this down. You select the learning rate is your initial learning rate divide by 1 plus t, and then you do the perceptron learning, perceptron update. And now there are two options. Option 1, let's call that option A, is you set t is t plus 1. That is inside this loop. Option B is here. You set t is t plus 1. One of these two might be the, you can, so essentially what's happening is in option A, you're incrementing t for every example. Oh, my TA just confirmed for me that the extra credit is worth 10 points. So in one of the options, you are incrementing you're incrementing t at every single example. In the other option, you're incrementing t at every epoch. In your homework, when I checked, it seemed like it was asking you to do option A, in which case actually the performance does drop quite a bit, because what happens is if you plot the learning rate as learning proceeds, it drastically drops down to zero. This is zero very, very quickly. If you want to play with this a little bit, move this update of the increment of the learning rate outside to this, to this loop here, so that you don't increment the t every step, but you increment t. You don't increment t for every example, but you increment t for every epoch, and that should not give you a bad. That should probably be better. You can use the epoch value as t. Essentially, that's what it boils down to. If you increment t here, you're using the epoch value as t. So in the homework question, it seems like we had asked you for option A, but we're going to assume that you can do either option A or B, and it will be fine. And it might be if it's okay. So then the next question is what happens if you what happens to the results? But before we go to the next question, Jeremy, does this give you a clue about where things might be falling off? Okay, so so it was option. Maybe there was okay. Now I thought it was option A in the homework, but I really wanted option B. If it is option B, then it should be. Then the homework is correct. So there was a. Can we take a poll? No, there's no poll here. It's just option B. Uh, um, no, it's not. It's not an option. I would suggest you just do option B. So there was another question here. Is there any reason? No. So what's the usual effect of accuracy and in terms with decaying the learning rate? Mine drops a fair amount, and I'm not sure if it's normal. That seems like the previous question. So, the next question is the results are still slightly worse, even though you're using option B. And that might entirely happen. There's no reason that that might not happen. The results might be worse. So when we talk about stochastic gradient descent, you will notice that actually all of this, everything that I've written here is actually an instantiation of stochastic gradient descent. And so I will talk about this a little bit more in detail. It turns out that the learning rate update can be a rather fancy game. And there's a lot of work that happens in all these things. You can the update that I have here, the R is the simplest version of things, but I'm not going to get into too much detail, but performance might drop a bit. Don't worry about it. I'm not saying it should drop a bit, but based on your random seed and your initialization, it might drop. So as long as it's in the same ballpark, it's okay. And we can use you can use Canvas to kind of poll people to see if this happens. So Parth points out that it says both option A and option B. Okay, so maybe I read the part that, okay, good. So in that case, we will treat either one of these as the correct answer. The intention was it should have been option B, but looks like it was mentioned in two places and we corrected it only in one place. So it's fine. Okay, so my TA offers a clarification. The first version had option A. We fixed it the next day, but some people downloaded the homework right away. So if you have not yet submitted the homework and you have the time and you did option A, fix it to option B. If not, put a note on Canvas saying, look, I did option A because I did that. We'll not, if we look at your code and we find that you did this, we'll not penalize it. All right, any other questions about the homework? Does the seed affect the accuracy? It probably does. The random seed probably affects the accuracy, but in a perfect world, it should not do it by too much. And there's a good reason for this. Without going into too much detail, the perceptron algorithm, the version that you implement, the batch perceptron algorithm, is actually Also, if you look at the algorithm with a different lens, which we will do in a while, the perceptron algorithm is actually solving a certain optimization problem. That particular optimization problem has the property that it doesn't depend on the initialization. The solution doesn't depend on the initialization. And if you start at different points, you'll essentially converge on roughly the same answer. So the seed should not affect the accuracy drastically. But here is a useful point, though, that is worth keeping in mind. A lot of learning algorithms involve randomness at some level. It's not deterministic. As a result, there might be mild variations. It should not be massive. For perceptron and say algorithms like SVM, there should be minor variations, but not a lot. If you see huge jumps across different seeds, then that suggests something is unstable, and such instabilities do not exist in the perceptron algorithm. They exist in other algorithms. When we talk about neural networks, we'll talk about that, but they don't exist in the simplest neural network, which is the perceptron. So you should see at most minor changes. So yeah, so this is comment about option A and B, and maybe there is like still some confusion. Like I said, when you write your report, just say which option you used, and we will grade it according to that. All right. There's nothing else. I would like to move on to today's lecture. Are there any other questions? There don't seem to be any. Oh, so for the extra credit, we get 100% accuracy for epochs greater than equal to 16. I think it's because we asked to use the same hyperparameter as average perceptron. Maybe I'm surprised about that. Ashim, maybe you can answer that question, because we didn't get 100% accuracy, though it's possible that there's some, maybe Ashim, you should take that question. Oh, 100% on training is fine. 100% on training is over. Oh, okay. So I see training. 100% on training might happen because it is overfitting, basically. Yeah. That's fine. That's not. I mean, that just means that feature space is so big that it can essentially learn the noise in the data. So don't worry about that. And it's worth thinking about whether 100% on the training is a fruitful thing. For the purposes of the homework, don't worry about it, but in general, it's worth if you see 100% training accuracy, it's worth thinking about that. What might be problematic is if you get 100% test accuracy or 100% cross validation accuracy, in which case one of two things is happening. Either your problem is so simple that you just learn it, or you just happen to have the right features, so you just learn it. So that's one thing that can happen. Or you have a bug in your code. The most common kind of bug that leads to 100% accuracy is the following. You have a feature whose value is the label. If you have a feature whose value is the label, any reasonable learning algorithm will get 100% accuracy. Of course, it's not going to generalize. It's just looking at the label and saying that's the label. So that's not saying much. So yes, of course, not on the test. All right. So let's get started with today's lecture. Today we're going to look at least mean squares regression. So we've been looking at classification a lot with linear models, with the perceptron and its variants. Today the plan is we'll spend some time talking about regression, and in particular linear regression. And some of you I know have already seen linear regression before, but I want you to kind of think about, you may have seen it in a different context, and I would like to use what is in essence a rather simple task, namely regression, to introduce a concept that we will be using quite a bit going ahead, which is thinking of learning as just optimization. So So I'll start the plan for today is we'll start off with some examples of of regression, and then we'll talk about the optimization problem that we'll solve, the least mean squares objective, and then talk about the gradient descent perspective, and then introduce for the first time in the semester an algorithm called stochastic gradient descent, which is which is the simplest form of a family of algorithms that drives today's state of the art machine learning. So let's start with some examples. Let's say we have a task where we want to predict the mileage of a car from its weight and age. I understand this is probably not a great task, but let's say we want to do it. And to do that, we will collect data of different cars. So we have 4 examples here. And the output, which is this mileage column, is a real number. It's a positive number. Let's pretend that we are not going to worry about that. So what we want is a function that can take these two features, x1 and x2, and predict this number here for every car. So the instance space corresponds to 2-dimensional inputs. The label space corresponds to real numbers, positive numbers. Now, we should ask ourselves, once we see a problem, what is the hypothesis, that hypothesis space that we want our learner to explore? Since we are talking about linear models, and also more reasonable, more also because it is a rather easy hypothesis to assume, we can assume that the output is predicted with the linear model. In other words, the output is simply a linear function of the inputs. Now, each linear function is parameterized by a collection of weights, the weight vector, and the goal of learning is to, of course, to discover them. Now, so once learning is done, just like in the perceptron case we've seen before, the learning algorithm would produce a single weight vector W, and once we have that, at prediction time, we can use the values of these features for a new car and predict the mileage using exactly this expression. It's simply the dot product of the weights and the features. Notice, however, just as a notational thing, I have included a bias feature as the first weight. So this is the strategy that we're going to pursue. We are going to treat the output as a linear function of the input and try to learn the parameters that control that linear function. More generally, for linear regression, the input is a vector, which x is a d-dimensional vector, and the output is a real number. When we assume here x, we'll assume that the first dimension of x is a feature whose value is always 1. This just makes it easy so that we don't have to worry about the bias and such things. So this is the same trick that we've seen before, where the bias is folded into the weights. Given this setting, we are still in the supervised mode of learning. So we are assuming that we'll get a training set of this kind. It's a set with a bunch of examples. Each example is a pair. It consists of an input vector, xi, and its corresponding label, yi. The label is a real number. Nature has produced this real number in using whatever mechanism it wants. What we assume is that nature is using a linear model to produce these real numbers. So y is simply w transpose x, where w is the learned weight vector. Both w and x are d-dimensional vectors. That's why you can take a dot product. So this is a rather simple strategy, but it's so commonly used that you've almost definitely seen it, whether maybe you've not seen it with this name, but you've definitely almost seen it, where you're trying to, for example, this is a one-dimensional input where we have a single feature x and a single label y, and the goal, and you may be given examples of this kind, and you say that yeah, there's this trend. You're predicting y as w1 plus w2 x2, and when a new example x comes in, you predict its label by looking at the corresponding y according to that line. This, of course, it's important to note that the linear function is not the only choice we have. You could, of course, have chosen a different function. In fact, if you know something about the problem where the underlying system that produces the labels is not a linear thing and it has a certain other kind of a nonlinear interaction, you should probably incorporate that in your choice of functions. You could have, for example, used some sort of a polynomial to fit the data. And all of these are, it comes down to understanding the domain. This is not just true for 2 dimensions, it's also true for, sorry, with 1 dimensional input, it's true for higher dimensions also. With if you have 1 dimensional inputs, linear regression involves finding a line. With 2 dimensional inputs, linear regression involves finding a plane. With higher dimensional inputs, of course, it involves, as always, finding a hyperplane. This is the standard naming terminology, the naming pattern for anything in higher dimensions. You put the word hyper in front of it. So, you have cubes and hypercubes, spheres and hyperspheres, and you have a plane and hyperplanes. So it's basically, if you have a d-dimensional object, it's a d-dimensional inputs. The output of linear regression is a d-1 dimensional object. So any questions about the definition of linear regression, or just the problem statement? So anytime you encounter a new problem, you need to think about, and a new hypothesis space, you need to understand the following things. You need to know what is the function, what is the functional form. With decision trees, the function was actually a tree. With perceptron, the function was you take the dot product and you take the sign. With linear regression, is the function involves just taking the dot product. The other thing you need to know is how do you make, what kinds of things do these functions express? Just you need to understand that, so that when you actually use this in a data set that you may, or on a task that you care about, you can actually see whether this kind of a model fits the assumptions of your task. Or alternatively, if you don't know anything about the task, you should understand what kinds of functions this expresses so that you understand where it might fail. The other reason why it's useful is it gives you a very useful debugging tool. If you're going to learn a linear classifier, you better, you can use a linear classifier, a data set, for example, that's linearly separable to debug your code. If you're learning linear regression, you can use a data set that is, that fits the hypothesis to see if your learner recovers it. So it's a useful debugging tool. So you need to know what the functions are. You need to know what kinds of things it can express, what's the functional form. And as you're seeing this, it might also help to think about how you might implement this in code. Any questions about what, just the definition of the, or the signature of the problem? What about fitting a line in a 3D space? I don't know why you would want to do that. A line in a 3D space is also a plane that's aligned with one of the axes. So it essentially you're ignoring one of the features. So it's a special case. So the question was, what if I have 3 features and I want to fit a line? So if you have 2 features, let's say, I'm going to fit a line. So you have x1 and x2. I can say w1 x1 plus w2 x2 plus w0. If I say that w2 equals 0, that's a special case of this thing. So that just gives me, that ignores this feature, and that's your line. So it's not a, it's inside the space of things that we're considering. Okay, so now let's then look at the problem of how do we learn. So the third thing you need to know how to predict, how to make a prediction. What's the function? You need to know how what kinds of functions it expresses. And the third thing you need to think about anytime you see a new class of functions, new hypothesis space, is how does learning work? And for that, that's what we're going to spend the rest of today's lecture on. The goal of learning is to find the best weight vector given a training set. So So what does it mean for a certain weight vector to be the best? Let's maybe think about it slightly differently from how we'll approach perceptron. In perceptron, when we were thinking about the best weight vector for the classification task, we first produced an algorithm and then said, oh, look, this algorithm is good. Now what we're going to do is define what is good and then try to construct an algorithm around that. So for us, let's say we have an input xi and yi. For this input, we can ask, how do you measure error? It is a regression problem. So yi is a number. So maybe it's the number 21. And let's say we have two candidates for weight vectors. Let's say this is W. Let's say this is W. And W gives me a value of W transpose X is, let's say it gives me 20. And W prime gives me 40. Naturally, W is a better vector than W prime because it gives me a number that is closer to this. So I can ask, what is the cost of a mistake? The cost of a mistake for W is 1 because it's just 1 away from the target. And the cost of the mistake with W prime is 19. Effectively, you can write down the cost of a mistake is just the difference between the true label and the predicted value. But the difference could be negative, so you take the absolute value. So the cost of the mistake is the absolute value. Usually in practice, what we do is we don't take the absolute value, we take the square. So instead of this, we take yi minus W transpose xi square. Now, given a certain data set, I can ask, how good is a weight vector for this data set? One way of doing that is to add up all the costs over every example in the data set. The cost is the squared error, so I add up all the squared errors. So for every weight vector, this j is a function that produces a number. It's the sum of all the squared errors that this particular weight vector causes in the entire training set. You add them up, you divide by half because we will see that we are going to take the derivative of this function, and the derivative of a square will give you a 2, and this is just so that in your code you don't have a bug by forgetting the 2. So if you add the half, and adding the half does not change the ranking of the classifiers, it's a constant. So if not a classifier, a model. So if one model had an error of say 100 on a data set by just adding them up, the other one had an error of say 50, adding a half, multiplying by half just preserves the ranking. So it's 50 and 25. So this is called this thing here is called the squared error of each model. Sometimes it's also called the mean squared error, though it's not. What I've written here is not the mean. If I divide by m, I get the mean squared error. This is the total mean squared error of this particular weight vector on the example. So now this is the sum of the losses. One strategy for, by the way, I use the word cost here. These days, the more common terminology for this is loss. So for every example, the loss is the squared error, and what we have here is the mean squared loss. Next, we can ask, what's the goal for learning? A reasonable strategy for learning is to find the weight vector that has the minimum cost on this particular data set. Once again, learning is a search problem. So we are searching for weight in the space of all possible weight vectors, and we need some sort of one is find the weight vector that minimizes the total cost of predictions on the data set. just to kind of write this slightly more formally, we get this expression. We get what's the objective for least mean square regression. We want to minimize over all weights the total squared error, or the mean squared error, um, the average and the sum are only off by a multiplicative factor with respect to a constant, so they are equivalent. So we are minimizing the mean squared error, and this minimization problem, if we were kind of naive about it, we could just essentially search over every possible vector W, in some sort of a naive way, and answer the question. However, we will see more sophisticated ways of doing this. So there is a question: why is the square of the error used and not the absolute value? Here, I introduced the error as the absolute value and then quickly moved into the square. Is it because it amplifies larger errors? Actually, that's not the reason. The reason we use the square is because what we will do next is we will start taking derivatives of this function. The most important tool that we will use across a lot of learning algorithms is the ability to take derivatives. So calculus is going to be our best friend. And this function here is not differentiable at the origin, at when the absolute value is 0. So instead, we use the square because it's differentiable, and that just makes our life a little bit easier when we actually come to implementing the learning algorithm, which should be actually very soon. So our goal is to learn this is a new kind of a learning philosophy. Rather than saying, as with decision trees and with perceptron, rather than saying, here's an algorithm, let's see what it does. What we are saying here is what I declare as the objective of success. And I'm going to, or actually it's not the objective, this is the failure, right? It's the cost, it's the loss. And I define learning by setting up an optimization problem where I say, my goal is to learn by searching over all possible weights and finding the one that has the lowest weight. This is a declarative statement. It's not an algorithm. It's just a declarative statement. It's just saying, here is what I declare to be a good weight vector. If the solution to this problem was W star, I don't care how you got your W star. Maybe you searched over every single weight manually. Maybe you used this particular algorithm, or maybe you used that particular algorithm, or maybe you solved this problem on paper. I don't care how you do it. However you do it, if it satisfies this thing, it's least mean square regression. We will see this philosophy more often as we go along after we finish the theoretical part starting next week. Different strategies exist. Let me go back to the objective. There's a question: should we take the square root? No, you don't want to take the square root. I mean, if you take the square root, what will happen is we will see very soon, the square root of this function. If I put a big square root here, that just makes the whole function very painful to optimize. Once again, taking the square root does not change the ranking of the classifier. So we will just preserve this form because it's simpler to apply calculus to. So there are different strategies for learning. The most popular approach today involves gradient-based learning, gradient descent, or actually the most popular algorithm is some variant of what's called stochastic gradient descent. So it's an algorithm that will just do something to the data using the gradients, do something to the model, and at the end, it will produce a weight vector that comes with a guarantee that it's solved the problem. However, and I should point this out, very important thing, for this very specific objective, not only, but for this very specific objective, there is an analytical solution. You can solve this minimization problem on paper. You don't need a program. You can just solve it on paper in terms of the X and the Y. You can find a W that's the best in terms of X and Y. If you've never done this before and you want something fun to do and or challenging to do, I encourage you to work it out. You don't need gradient descent for solving this optimization problem, but you could. This presents a fantastic opportunity to introduce gradient-based learning. So that's what we'll do. So, are there any questions about this objective or this idea of learning by optimization? We will encounter learning by optimization a lot going ahead. We will see how support vector machines are learned that way. Logistic regression is learned that way. Naive Bayes actually is also can be seen from that perspective. And all neural networks today are learned through this philosophy, where you set up a loss and then ask an optimizer to find the best parameters that give you the lowest total loss over a data set. So are there any questions? Okay, there don't seem to be any. So what I'm going to do is now talk about the gradient descent algorithm for this particular problem, and also more generally. Gradient descent, some of you may have already seen gradient descent, and if you have, this should be just a recap. If not, this is like a first introduction. It's a general strategy for minimizing a function that is differentiable. Let's say you have a function j whose derivatives you can take. This j might look something like this. What gradient descent does is you start with an initial guess for w. It could be something like this, w naught here. And at w naught, this function here, if you zoom in, it has a certain value. So it might have some value like this at w naught. Now, this function, this is w naught here, this corresponds to w naught and the value of the function. This function is increasing in this direction and decreasing in this direction. We can ask, which direction is it increasing the fastest in? And then decide if it's increasing fastest in this direction, you take a step in the opposite direction. The gradient of a function defines the direction in which it grows the fastest, and you take a step in the opposite direction. If you want some sort of an intuition, think about climbing a hill or going down the valley between two hills. And imagine that for some reason, your goal is to go to the bottommost part of the valley, somewhere here. What you do is at every step, let's say you don't get to see far away. You only get to see the local neighborhood around you. Let's imagine you're in a fog in the mountains. You can only see around you, and the only piece of information that you get is which direction locally seems to be growing the fastest, going up the most. And so then you want to, the intuition is you want to take the opposite direction. And if the valley satisfies certain nice properties, then you're guaranteed to get to the bottom. Because at every step, you look at what's the fastest direction going up and what's the steepest direction going up, and you take a step in the opposite direction. It's very convenient that we live in the mountains because this analogy doesn't work in other places, or does not have the same intuitive understanding in other places. So at each step, what you do is at w naught, you have an initial guess, w naught, and you look at the gradient. In this case, the gradient is pointing up in this direction, or actually the basically w naught increases, the function increases if w moves in this direction. And so you take a step in the opposite direction and you get a new estimate. You get a new estimate, t plus 1 from wt. You keep doing this from w1, you go to w2, w2, you go to w3, and so on, till at some point you have declared that your steps are so small that it's not worth taking any more steps. You declare that you have converged and you move on. In general, this will take you all the way down. So this is an intuitive intuitive version of gradient descent. Of course, if you want a more formal introduction, and if you find this kind of this line of thinking to be exciting, or you want to know more about this, I encourage you to take a class in mathematical optimization. It's kind of fun, and it's worth knowing this stuff simply because it is it's the bread and butter of modern machine learning. I believe actually that the class on convex optimization is being taught exactly at this time. So of course, you're not going to be in that class and this one. Are there any questions about this, especially from people who've not seen this before? Because if you've not seen this before, this may be a little complicated. This is not the Newton's method. This is definitely not the Newton's method. The Newton's method requires a second derivative. Here, we are only calculating the gradient. We are not calculating the Hessian. So the only piece of information we have at every step is which direction is the function going up the fastest, the gradient. And and we're going to use that to just do the keep iterating this all the time. So at every step in learning, first you compute the gradient. That is, you find which direction in this case is the function increasing. So in this case, this is a one-dimensional case. So W is only a single number. Either W can go this way or this way. And the gradient at W naught said, if W goes up this way, the function value is going up. That's why this line is angled this way. And you say, okay, if I go in that direction, I'll go to the top of the mountain. That's not what I want. So let me take a step in the opposite side. So any other questions? In principle, this is a rather easy solution. There are a lot of practical issues that are worth thinking about. In particular, one of the practical issues is the question that just came up: how far a step do we take? Now, that's a very good question. So let me go back to this picture here. Let's say we are in W2. We are currently, WT is currently here. We are at this point. Oh, by the way, another sort of a metaphor that I have seen being used that some people find very useful is to think of a ball rolling down the hill. So let's say this is where we are right now. Now, at this point, we need to take a step. We do the same thing. We compute the gradient. We see that the function increases in this direction. And we decide to take a giant step in this direction. We end up here. We are objectively worse than we were before. So the step size is an important practical consideration. And there's a lot of work in this space. We will talk about a formal criterion for how far the step should be. In general, if you take small enough step sizes, it should be good. This should look a lot like this decaying perceptron that you're implementing. By the way, when people never use the word decaying perceptron, that has a rather, that brings to mind something weird. So the decreasing learning rate that you're implementing in your homework would be a good strategy, because as you go along, even though you may take giant steps in the beginning, because the step size is getting small, you kind of you might bounce around between these two things, but over time your steps are getting small and you converge. So another question is, should the step size be relative to the magnitude of the gradient, the steepness of the slope itself? That's a possibility, but you have to be careful there. If your step size, let's not go there yet. I'm happy you're thinking about this, because it's a very interesting way of thinking about it, but let's not go there yet, because I want to keep the simple stuff in the beginning. The next question, the other practical thing is, why should this get to the bottom of the valley? What if there are more than one valleys? What if there's more than one valley? So let's say you have, instead of this nice function here, let's say you have a function that looks like this. If you start here, if the ball rolls down, it goes here. If you start here, it goes there. And if you start here, it goes there. So depending on where you start, you might end up in a different place. But the nice thing, we don't have to worry about that problem yet, because as we won't see this formally, but you can try to think about why this is the case. But that function there that we care about today has exactly one minimum. It has only one value. It looks like this picture here. As a result, no matter where you start, you will end up in exactly or around the same region of the parameter space. And yes, it's good. Anytime you see that kind of a thing, this is a convex function. Anytime you see convex functions, you should probably make happy noises, because um, it's a situation that means that you can actually get some guarantees. The function, this is convex function because it's essentially a parabola. Well, that's not the reason, but you can. These two things are very closely related. We'll talk about convex functions in a little bit more detail as we go along. Okay, so this is the general strategy for gradient-based learning. Let's instantiate this for the problem that we have for least mean squares regression. So as always, you initialize your W, and doesn't matter where you initialize, because if you have only one value, doesn't matter where you start, you will go to the same place. So, without loss of generality, let's say you initialize your W to the 0 vector. And then you iterate you iterate over multiple time steps. And at every time step, you do the same two things. First, you compute the gradient of J. J is this objective here with respect to W. It's really the derivative of J with respect to W. And I see that my slides, I hope, I thought I fixed it. I think the version on the website would be cleaner. There's going to be a lot of math issues here because I forgot to update my iPad. So this, we will call this nabla J. This is if you've not seen this symbol before, this is nabla. I'll just call it the gradient of J. So you compute the gradient at this point, and then you update the weights according to this rule. The goal, remember, what's the goal? The goal is we update the weights by taking a step in the direction opposite to the gradient. The gradient is something we've already computed. We take a step in the opposite side. And how big of a step do we take? The size of the step is R. R is the learning rate, just like we saw for perceptron. So we take a negative step with respect to the gradient, and the size of the step is R. For now, let's assume that R is a small constant. We'll get into what R is later on. So this is essentially what this means is the problem is solved. We know how to do calculus. We know how to compute the gradients. This is just vector subtraction. That's also easy. So in theory, the problem is done. At this point, you should be. We can technically pack up and move on to the next thing. Except this step might be a little bit complicated if you've not. If it is more involved than just that one line that's written there. So for the rest of today, I'm going to be spending pretty much most of the time talking about how to compute the gradient of this function with respect to W at this point. So before we talk about how to compute the gradient, are there any questions about the skeleton of the algorithm? Are all the dimensions orthogonal to one another? Yes, we're going to assume that they are. And any dependencies, yes, we're going to assume that all features are orthogonal to each other. Are there any other questions? And as much as I like class participation from those of you who are participating, I notice that there are many of you in class who don't participate. So do feel free to ask questions. It helps understanding. And as we have seen before, active learning is more effective than just supervised learning. So another question is, are features independent from one another? Once again, we're going to assume that they are. If you feel like in a problem that you think about, the features are not independent, that suggests that there are some interactions between the features that suggest feature transformations, for example. For now, we're going to assume that features are independent of each other. Can you explain where the samples of the algorithm come in? Where do the examples come in? So notice that, oh, let me keep this nabla here. Where do the examples come in? I have initialized the weights, I compute the gradient, and I update the weight. There don't seem to be any training examples. The training examples are inside the definition of J. The function J has been constructed for this particular training set. So basically we have the objective function J is called the objective function. The objective function includes all the examples and it's used as a batch. Yes. Does that clarify things? Any other questions? How do you initialize W? Do we pick an arbitrary number? If your function has this nice property that there's exactly one such value, it shouldn't matter how you initialize W. By the way, it's not a number but a vector. W is some, if you have D features, this is a vector in RD because you're taking the dot product of W and X. If your objective function has this special property of convexity, then your initialization should not matter. In this case, for gradient descent, for least mean squares regression with a linear model, the objective function is convex. So it doesn't matter how you pick your W, pick an arbitrary number or just initialize it to all zeros. You will get roughly the same answer. Okay, now let's maybe think about the one thing that is left, which is how do you compute this gradient? So let's think about what a gradient is. First of all, as a sanity check, it's useful to know that the gradient, so let's think about what this function W is doing. Sorry, J is doing. J is a function that takes a W and produces a real number. It's in general a function that takes a vector and maps it to a real number. A useful sort of a heuristic to keep in mind is the gradient of W is going to have the same shape as the input. In this case, the gradient, in this case, the function J, the input to the function J is a vector of size D, which means the gradient is also going to be a vector of size D. It's going to consist of all partial derivatives of the function with respect to each element of the weight vector. So in order to derive on paper the gradient of this function, all we need to do is, I say all we need to do, it's going to be a little bit of work, but all we need to do is just to compute the partial derivative of this function with respect to each W, let's say with respect to Wj. If I do this for all j, I can now construct this entire vector because I know every single element here. If I know each element of this thing, I can instantiate this algorithm because this is just a vector. I'm just adding two vectors, so life is good. So the gradient is the gradient of this particular objective function is itself a vector with as many dimensions as the input to the function. So the gradients of the form this thing. So let's maybe look at focus on one of its elements, the jth element. So the partial derivative of j, capital J, with respect to Wj is the partial. I've just plugged in this definition here, so there's nothing much shocking happening there. But some of you know how to compute partial derivatives of these things. Some of you may not. So I'm going to go through this in a fair amount of detail, bringing it down to basically simple calculus, and hopefully you will see that this is what we will eventually build is just notational conveniences on top of what we will see today. So the gradient of this function, the partial derivative of this function of a summation is simply the sum of the partial derivatives. So we can move this partial derivative inside. So we have the partial derivative of this square term. Let's the derivative of a square is simply x square is simply 2x. So it's 2 times this thing times the partial derivative of y minus w transpose x. But what I have done here is I have written w transpose x in a rather verbose form. Remember, w transpose x is simply w1 x1 plus w2 x2 and so on. But I have an xi here, so xi is w1 xi1, the first feature, i2. In particular, we only care about wj times xij and the whole thing that comes after. This is the term we care about. So we're taking the derivative of this difference with respect to wj. Everything is a constant with respect to wj except the term inside the circle. So the whole thing vanishes except this one thing. You should not forget the minus sign because every single wixi term, the wjxj term is negated. So we have minus xj. Now I can reorganize things a bit. I can cancel out the two, take the minus sign outside, and that gives me this thing here. So the gradient of the objective with respect to the jth weight element is this expression here. You sum over all the examples, the difference in the prediction from the prediction and the ground truth, and multiply the jth feature, and you negate the whole thing. So this is a single element in this vector. So we can compute the whole vector by, if you naively, if you don't care about efficiency, you can compute this vector by applying this for every single element of wj. So go from 1 to d and fill up the gradient vector. Are there any questions? Now, this is a fair amount of detail. So there are two kinds of questions that might show up. One is you just got lost in the notation. There's like, there's so much notation on the slide that you just got lost. Another thing is you forgot where we are and you want me to revisit something. So let me know what. So there is a question. Computing this is order of n square. What is n here? Computing this, oh, then, okay, d, you mean. So the d is the dimensionality. So for every, it's actually a little bit more than that because it involves this summation over the data, and this dot product might also be order of d. So order of d square, yes, times m. And this might be a little slow, but the good news is that our computers are built into these days with vector processing hardware that can do this super efficiently. And if you use a library like NumPy, this can be implemented quite efficiently. So what's happening between the second and the third line? And this is an important thing. So I'm going to go over it once again in some detail because we will encounter this idea a lot more. So let me go back to just the second line. So this is, and we only care about this thing. So let me zoom in on just that. So we had the partial derivative with respect to wj of yi minus w transpose xi square. So it's some function. Now it's any function. So remember, what's the chain rule of taking derivatives? So what's the partial derivative? Let's not worry about partial derivatives. Let's say the derivative of some function. Let's say x. Oh, we don't have an x. W plus 1 square. It's simply twice w plus 1. But instead of w plus 1 square, what if you had the derivative of, say, w square plus 1 square? Or let's not say w square. Let's say we have log w. I'm just making things up. I'm just making up a function here that's slightly more complicated. For this, first you need to take the derivative of the square. So it is twice log w plus 1 times the derivative of this thing, which is 1 over w. So this is the chain rule. In general, if you have the derivative of f of g of x with respect to x, it is okay. This is it's going to be ugly notation to write, so I'm not going to write that. But uh, what you do is you take the first we take care of the square and then go into the thing. So that's what we've done here. So the derivative, partial derivative of wi or wj with respect to this is first we take care of the square. So we move this thing out and let's worry about just the square. So the derivative of the square is yi twice yi minus w transpose x times the now you take the derivative of whatever is inside the thing of yi minus w transpose xi. But in the slide, the way I have written it is I have taken this one. Um, okay, good. So I'm glad you clarified that you are comfortable with the chain rule. So the next step is what I have kind of expanded out. We're not taking the derivative of the vector, but actually just the derivative of a single element. So if you, in general, when you take the partial derivatives of something with respect to an element of the vector, so you have yi minus, let's take the thing inside, w1 x1 plus w2 x2, and let's say we have only 2 dimensions. And I want the partial derivative with respect to w2. W2 is not a vector. W2 is the second element of W. So W is a vector that looks like this. As far as this particular differentiation is concerned, things like W1, Y, X1, X2 are all constants. So we don't care about them. So we can just, this is just a linear function. So the derivative of this is simply minus X2. Because everything else, this term is a constant, this term is a constant, X2 is a constant. And we are left, this is exactly the same as the partial derivative of, or the derivative of W2 X2. Now minus W2 X2. So that's what's happened here. I have expanded out this expression here. And only this term remains. And that's why only that term contributes to the derivative. Does that answer your question, Chris? Other questions? But it gave me the opportunity to talk in a bit of gory detail about the chain rule, which will become extremely relevant when we talk about neural networks. So it's a good good thing to mention, because if you are uncomfortable with what I just said, look up the chain rule, because we will revisit that. J is not the Jacobian. J is the loss. We will not touch Jacobians in this class. Yeah, we will not use the word Jacobian in this class because. So the thing to keep in mind is this is just one element of the weight vector of the gradient, and it has an interesting property. It's the sum of the error, meaning this is not the squared error, but the actual signed error and the input. It's not saying much. It's just a nice observation, which maybe back in the 50s, when people were thinking about this, they were excited by this this thing because it had some nice interpretation. But let's plug this in. We compute, first of all, in order to compute the gradient, first you evaluate the function. You compute W transpose X for every example. Once you evaluate the function, you can now compute the gradient by constructing the jth element of the gradient vector, and you do this for all j features, all d features. And once you have, this is just one element that's written here, and then you update the weights. This is just a vector. You update the weights with each element of the weight gets this thing subtracted from it, and this is the whole process of gradient descent for least mean square regression. Of course, you need to know how many steps we do. You go through this as many times till the total error is below some threshold. So you keep computing j of w here, and you there's some bookkeeping that you need to do. If the error doesn't drop drastically enough, and that's a hyperparameter that you decide, the convergence criterion. It's not a hyperparameter, it's an optimization parameter. You don't worry about it, you just fix it to some number. And if the error does not shrink by more than that quantity, you say that, maybe you've come down to the bottom of the valley, and so you don't need to take any more steps. Or alternatively, you compute the length of this gradient vector and you find that it's too small. Then you don't make a difference. You don't make any more updates. Because xj changes for every sample in the summation, you have to do that for every element. Basically, because xj is the jth example. So that's oh no. Yeah, because j changes for effectively instead of xj, xij, j changes, right? So you have to redo this because there's a j dependence here. So just to remind you, we still have not talked about the learning rate. R is the learning rate, and for now, pretend it's a small constant. This algorithm, and as I said before, is guaranteed to converge to the minimum of this objective landscape, objective function j, provided R is small enough. And the reason for this is because the objective is a convex function. I'm not going to talk about convex functions in any detail right now. We'll come to that when we talk about other learning algorithms. For now, I want you to think of it as a function that has a single valley and nothing else, and it's kind of smooth, and it doesn't have any local bumps that might confuse the learner. So this is simple gradient descent. Some of you may have encountered this before. Now, it turns out this has a fundamental problem. And fixing that is going to give us what used to be called incremental gradient descent, but what is almost unanimously called stochastic gradient descent today. And the problem is this summation that's highlighted here. To compute the gradient, I need to sum over the entire data set. And someone brought this up. This seems like a rather inefficient thing. The most inefficient part here is this summation, because imagine that you have a data set with 1 million examples. To just make one update on your parameters, you have to sum over 1 million entries, sum over 1 million examples, compute all these gradients. And this can be rather inefficient, especially because maybe even at the beginning of learning, your weights are so bad that even a small number of examples, even one example, tells you that this weights are bad. Don't bother summing through this thing. Just make an update right now. As soon as you see one example, you see that this weight is so bad. Just make an update. And this idea is what gives you this notion of incremental, of stochastic gradient descent. The problem is that the weight vector is not updated until all these errors are calculated. The intuition for incremental gradient descent is, why not make early updates? As soon as we encounter an error, if y minus w transpose xi is big, just make an update right there instead of waiting for the full pass over the data. What that means is this gives us this strategy. So for each example, you pretend that this particular example is the entire data set. So this summation has only one element. You pretend that this example is the entire data set you have, and you quickly make an update. If m equals 1 in this slide, inside the circle, the summation is over one element. So you can just compute this gradient for that example and make an update. And now you stop pretending that this example was the entire data set. You pick another example. In that case, then you pretend that example is the entire data set, and you make an update. To make an update, what you do is you calculate the gradient with respect to your data set. But this data set currently is just one example. You calculate the gradient with respect to that example and update the model. This is called stochastic or incremental gradient descent. And the contrasting thing is what we saw before, which was called batch gradient descent, which makes one update to the weight vector for every single pass. So you need a full pass over the data to make an update. The alternative is you take an example, compute the gradient, make an update. So it might look something like this. So you iterate multiple times, and then for each training example, you immediately update the W. So for every example, you calculate its gradient, which I've done here, and I'm showing here only the jth element of the weight vector. So the jth element of the weight vector gets updated by remember the gradient of j was minus yi minus w transpose xi times xi j. This is the jth element of the gradient, and the update is w minus r gradient. So these two minuses cancel each other out. That's why you have a plus here. So I take an example. Instead of waiting to calculate all the gradients over all the examples, I just take an example, compute the gradient over that one example, and instantly make an update. And I keep doing this where, in contrast to the previous method where the weights were updated after processing all the examples once. So there's a question. With stochastic gradient descent, would you want an even smaller learning rate than the full algorithm, which iterates over the entire data set? Yes, with stochastic gradient descent, the learning rates become slightly more important because each example is a stochastic, is a noisy gradient, noisy approximation of the full gradient. As a result, if you start taking giant steps, you might be moving around the optimization landscape quite a bit. So you want to take the learning rate has to be controlled carefully. What if the previous updated weight increases the loss? Exactly. This is the right point. So it's possible that a certain example increases the loss, but what we will see as we go along is in aggregate, this works out, which is kind of a very cool idea. Again, it's another idea that originated in the 50s. Even though any single step, at a single step, you might be locally making the wrong choice. In aggregate, you kind of wander around the optimization landscape and converge really fast to the optimum. This update rule, so there is a NumPy update, and it almost seems correct. There's a learning rate missing. This particular rule was invented long back, and it in the neural network literature, it used to be called, it's less popular now because it's basically stochastic gradient descent, but it used to be called the Widrow-Hoff rule in the neural network literature. In general, online, this must look very much like an online learning. Where you take an example, must look also similar to your the perceptron you've implemented. You have multiple epochs. For each training example, you do something. What you do depends on what problem you're solving, but this sort of an incremental or stochastic gradient descent is much better if your data set is large, and it gets much faster. It gets closer to the optimum much faster. There's a whole cottage industry around learning rates, and this will be the last thing I'll talk about today. In general, the learning rate must decrease to 0 to guarantee convergence. This is not the non-separable case. Let's ignore that. The learning rate is also called the step size, and there are many different sophisticated variants of what the simple strategy that you're implementing in your homework. Of course, choosing a better starting point is better because you'll get faster, you'll get to the optimum faster. But if you don't, for the convex problem that we have, it's okay. These are simple algorithms, and almost every algorithm that we see from now on in the class can be traced back to this simple idea of stochastic gradient descent for different kinds of loss functions, for different kinds of hypothesis spaces. And this is like a fundamental building block of modern machine learning. Let me wrap up. We spoke about linear regression, but I use this as an opportunity to introduce you to the idea of learning by minimizing a cost. What we want is to predict a real number, and we assume that the output's a linear function of the inputs. We saw gradient descent, we saw stochastic gradient descent, and you should understand this. And we will revisit this idea a few times. Hopefully, you'll think about questions when we see this again. This particular optimization problem, however, as I said, does not need all of this heavy lifting. It can be computed the solved directly by on paper and written as a matrix problem. So I'll leave this as an exercise. So for I'm going to give you two exercises that you should think about. Write down the gradient descent algorithm to solve that mileage problem with those 4 examples. Just work through all the details so that you get a sense of what's going on. And also, if you want a slightly more challenging thing, it turns out for least mean square regression, you don't need to use stochastic gradient descent at all. This particular closed form solution just works. So in order to do that, you should solve this optimization problem that you can do offline. The reason for least mean square regression, the right thing to do would be to actually use the closed form solution. But for other kinds of regression, when your classifier, when your model is a neural network, you don't have a closed form solution. That's why we need the general algorithm. Okay, I'll stop now. I'm a minute over time, so I'll probably not ask you to ask me questions, but think of questions and we'll pick this up. We'll start with computational learning theory in the next lecture on Tuesday. All right, thank you, and I'll see you on Tuesday.